Yeah, so good evening, all, and welcome back to the third week of TA live sessions for AI SMPS. So, before we start, am I audible and is my screen visible? Okay, thanks for confirming. So, sorry for that. Yeah, so today we'll be discussing some questions from week 3 of the course, where we'll be discussing some applications of DFS and BFS that we learned in the last week. And we'll also see some more heuristic based methods like best first search and hill climbing and so on and so forth. Okay, so yeah, sure. Before we get started, yeah, you can ask your doubts. Please go ahead. Okay. Uh-huh. Right, right. Reg- Regarding the traveling salesman problem, you mean? I see. Um, so I was planning to discuss more of traveling salesman problem in the next live session. Um, yeah, yeah. Okay. Let's do one thing. Let's yeah, yeah. Let's do one thing. Let's discuss the questions there we have in the slides, and then after that, let's have a brief discussion of traveling salesman problem as well. Does that sound fine? Okay. Okay. Anything else before we get started for today? Okay, cool. Then let's go a bit faster through the first few questions because yeah. Yeah, that's right. Two sessions that were conducted by me. So there is another TA who's also conducting live sessions on Saturdays. Yeah. So I think both of us are in our third weeks. So we are going in tandem with the co. Yeah, yeah, yeah. So we are going in the same pace as the course. So for each of the 12 weeks of the course, we will have one live session. Okay. Okay, so there's a few doubts in the chat box. So in breadth first search, move gen returns nodes in alphabetical order always? Not necessarily. In both cases, in TFS or BFS, whatever move gen or whatever order move gen gives us, that is the order in which the nodes are returned, or no, the order which we follow. It's not necessary that they have to be in alphabetical. They can also be alphabetical. We will see one example of alphabetical ordering in today's questions, and I think that will help you clarify your doubts. So yeah, that's about it. And we will discuss heuristic questions as well. So I am keeping this doubt until we discuss that question. Uh huh. We have we have a question from Beam Search as well today. Yeah. So one thing that I'd like to share before we get started with the questions is it would be great if you could like you guys could post your requests on the discussion forum maybe a week or maybe at least 2 3 days before the live session, so that then in that case I will also have enough time to prepare questions accordingly, right? So that will help both of us. So yeah, for going forward, if you would really like one of the topics to be discussed, then just make a small post about it on the discussion forum, and I'll have a look at it, and then we'll incorporate the questions accordingly. So but yeah, for today I think that the questions we have should cover some of the queries that you have requested. So so there's another request for depth bound depth first search. Today we don't have a question on DBDFS, or even on iterative DFS also we don't have a question right now. But yeah, based on the questions we have today, try solving it, and if it's unclear, maybe next week we can take those up. Okay, so let's get started for today. So this is the map that we are going to be using for all the questions that we are going to solve today. Okay, so here make a note that S over here is our start node. Okay, so these different nodes are represented by different alphabets. Okay, S is our start node and G is our goal node. Okay, so our aim is to go from start node to the goal node, and for achieving this we are going to use several different methods. We are going to start with depth first search, breadth first search. We are going to look at best first search. We are going to look at hill climbing and see how the methodology changes across these different methods. Okay, so okay, so I hope this is clear. Let's go to the question then. So the question says that in the map starting with node S, list the first 7 nodes inspected by depth first search algorithm. Okay, so you have to start from S. Okay, and you have to list the first 7 nodes that DFS is going to explore. Okay, and note some additional conditions that are given to us. Okay, list the nodes in the order they were inspected. Okay, that means that you have to start with S, because S is where we are going to start with, then write the node whichever we are going to explore after S, then so on and so forth. Okay, in case our algorithm terminates before we even explore 7 nodes, then we have to just report those set of nodes that we explored up until the point of termination. Another condition is that here the alphabetical part is coming up. So here remember, we are not given the movegen table, right? Instead we are told, I have not explicitly mentioned in the question, but it was a part of the question that I have not written over here, is that we are going to follow alphabetical ordering of nodes over here. For example, if we are at node S, okay, so S is connected to E, K, O and J, right? So imagine that the movegen table has S, and the nodes that we could go to from S, E, J, K, O, they are in alphabetical order. Okay, so that's then you can build up your movegen table based on this graph. Okay, so is the problem setting clear? Okay, then I'll give you a couple of minutes to try to solve this, and then we can discuss the solution. Also, I would request participants, they can switch off their videos. That will help save us some space for the video recording. Okay, so I still see there are a couple of people who have switched on their videos. I'll really request you to switch off your videos. I hope my screen is visible now. Mr. Srinivasa Rao, I would request you to please switch off your video. Okay, while sir is figuring it out, let's go back to the question. Okay, so any answers yet? Okay, so we have a couple of answers. SEABCDI. Okay, so let's have a look at the question. Okay, so remember that here we are told that we are going to follow a depth first solution. Okay, we are going to start with S. Okay, and so for this question we are not going to do the whole building of stack and open and close list. Okay, because this is a question that we can solve very easily without even constructing everything. Of course you'll get an understanding of the whole procedure if you draw the make the open close list for your own understanding, that you can do at your own time, but today I'll just show you a quick trick. So we start with S. Okay, and from S the nodes that we could go to are E, J, K and O, right, in that order. And because we are following an alphabetical order, E will be the one that will be at the top of the stack, right, because DFS uses a stack. So E will be explored next, right? So after S we will go to E, right? Now E is connected to S, A, B and F, right? Out of all of these, A is the one that comes first in the alphabetical order, right? So A is going to be explored next. Remember, depth first search follows picks a particular direction and goes all the way to the depth, right? And if it's not able to find the goal, it backtracks and then again goes to another depth, right? So here it picked up after S it picked up E, after E it picked up A. Okay, then A is connected to J, E and B. Out of these, B will be popped up next, right? So after A, B will be explored, then C, then D, and after D, I will be explored, right? And at this point we have explored 7 nodes. See, S, E, A, B, C, D and I, right? So the answer would be S, E, A, B, C, D and I. So yeah, is that clear? Any doubts in that question? No, it's okay. You're yeah. Mm-hmm. Why do see, so here we are thinking of closer in terms of the location, the map that is given to us, right? But when you implement this program in terms of a code, there you won't input this image to the method, right? You just input the set of nodes that you have to whom they are connected, right? So our code won't know which is closer, which is far away until we define a certain heuristic that gives us a measure of how close or far a particular node is from the goal, which we will also see in one of the methods that we are going to discuss. But this method DFS that we are picking up, the property of this method is that it picks up, like I was saying, it picks up a particular direction to explore and it goes all the way to the depth of that direction until and unless it finds the goal or it finds out that it hasn't reached the goal. So it will backtrack and it will go explore another direction, another depth, right? So I'll maybe show it diagrammatically. Just give me a moment. Right, so consider this is your start node. Okay, your DFS will go around and this is your whole set of uh, search space. Okay, different nodes are a part of this. So DFS will go in this direction, then it will go in this direction, then this, it will keep on exploring like this until it reaches, let's say, this point and it cannot go any further. Okay, then it realizes that, oh, I can't go any further and I also haven't reached the goal. So it will backtrack. Let's say that it will backtrack to the first option that it had and it sees that, oh, from here I could explore another depth, right? So it will go and explore another depth like this, and let's say finally over here it reaches the goal node, and then it will stop. Okay, so this is a property of DFS, that it will pick a particular direction, it will go into its depth. That's why it's called depth first search. Whereas what would happen if we had a breadth first search algorithm? Let's say we have a similar search space. Let's say this is our start node. So what this will do is, instead of going to a particular depth, it will first explore its neighborhood. Okay, so it will go on exploring its neighborhood like this, like this. There are nodes in the path. Okay, so it's first exploring its neighborhood. It will keep on expanding its neighborhood until and unless it reaches some point where it has encountered the goal node. Okay, so it's because of the inherent property of the method that we are using, is we are following S then E and then A instead of going to F, which seems it's closer in direction to the goal node. So does that help? Yeah. Yeah, the next question itself is based on breadth first search. Yeah. Mm-hmm. Sorry, can you come again? Mm-hmm. No, no, no. After going to A, after S, we are going to E. After E, we are going to A. After A, we are going to B, and after B, we are going to C. Yeah. So this is the order in which we are exploring the different nodes. Okay, it's not necessarily the most optimal path from start to goal. Okay, this is just the order in which we are exploring the nodes while our method tries to reach the goal node. Yeah. Yeah. Mm-hmm. Yeah. Yeah. Okay. Mm-hmm. So yeah, we will be uh, it will follow the elements that it is having in the order in which in which it is having in the stack, right? So remember, this will be following a stack. um, Khalid, maybe you can mute yourself, and once we have discussed this particular solution we can thanks. Okay, so yeah, it's maintaining a stack, right? So first, S is the only element in the stack, right? Once S is explored, S is removed from the stack, then we insert E, J, K, O in that order, right? E is at the top, then we have J, K, O. Okay, then E is removed. Okay, once E is removed, uh, then what which elements are in the vicinity of E? Let me enlarge this. Okay, so in the vicinity of E we have S. Now S is already in the closed list, right? So we won't add S to our stack. We can add A, B and F. Now you are saying that instead of B, let's say this is Z. Okay, at the last thing in the alphabetical order. So this will be entered in this particular order. We will have A, F, Z followed by J, K, O. Okay, because JKO is also part of the stack from the time when we added S, right? Right, so after that A will be popped. Okay, then A will be popped, and after A we see that we can't add anything new because A is connected to J and let's say Z over here, and E is already in the closed list, so we can't add anything else. So we will pop the next element that is there, which is F, right? So then it will start exploring from F onwards. It won't go into that loop. So this is the property of depth first search. It will backtrack when it can't find a solution, right? If it gets stuck at some point, it will backtrack and then it will explore the other option that it had available. Yeah. Yeah, Khalid, please go ahead. Mm-hmm. We can check. So we were at I, right? After I, what is the, where can we go? After I, we can uh, okay, we'll have to take a look because I is connected to H also, right? And H would have been added at some point in the stack because when we explored C. So we'll have to go through the make a whole open and close list. Let's look at the elements that are there in the stack and see if it finally reaches the goal. But I would suggest, why not? Why not? Can you? Sorry. Yeah, you can use any strategy you feel comfortable with, either the open closed version that we discussed in the previous live session or the one that you are referring to. But I would recommend let's do this offline so that we can move through the questions, because you already spent one whole session on DFS and BFS, right? I want to give some time to the other methods as well. Okay. Answer as to whether we can reach goal from S using DFS, right? That's what you're asking. That's what I'm saying. So the first 7 nodes is what we explored, right? After that, what we have to do to understand what node is visited next, we have to make a detailed solution, right? So that's what I'm saying. It's better to do that offline maybe, and then if there's any confusion, you can let me know. Yeah, there must be a solution. So yeah, just explore it. If you encounter any obstacles, please let me know. Okay, so I hope that covers all the doubts that were asked in the chat box regarding this question. Let's go to the next question, which is based on breadth first search. So the same map, same problem. We have to go from S to G. Move gen table is the same. Everything is the same. Just the method changes. Instead of DFS, we will explore BFS, and we have to list the first 7 nodes that will be inspected. Okay, remember this will follow a queue. So again, I'll let you. So we already have a couple of answers. That's great. Um, I'll just wait for maybe a minute and then we can discuss the solution. Okay, so we have a couple of answers. Let's have a look at the solution. So here we will follow a breadth first search, right? We will explore the neighborhood first. So um, yeah, so we will start with S, of course, and then E, J, K, O. These are the neighbors of S, right? and these will be inserted in the queue in the order EJKO, right? So first S will be explored, and because EJKO will be inserted in the queue, then EJKO would be explored in that specific order, right? We can be sure of that, right? So after S you will have E, J, K and O. Now what would have been there in the queue after EJKO? That we can guess based on what would have happened when we explored E, because after S we will explore E, right? Because that is the next node that comes in alphabetical order. And while we were exploring E, we would have inserted A, B and F into the queue in that order. So we would have S, E, J, K, O, A, B, right? And this completes 7 nodes that we have to inspect. So the answer would be S, E, J, K, O, A and B. These are the first 7 nodes that will be inspected by breadth first search. So I see many of you have answered this. That's great to see. I hope there are no doubts here. If there are, please let me know. Okay, that's great then. Thanks for the confirmation. So if this is clear, let's move ahead to the next question for today. So these are the two questions we are going to discuss related to DFS and BFS. Okay, and I think they should give a good robust idea to you. Now let's move on to heuristic based methods. Okay. So as one of your colleagues had pointed out, what if we have a heuristic? Okay, basically you can think of heuristic as a function. Okay, and this function will tell us for each node how let's say how good it will be for us to explore that particular node, and how we can define that is in terms of how close that node is to the goal node, right? So for example, the distance of the goal node from itself we can say is 0, right? Do you all agree with me over there? Okay, that's great. Now we have to think of a way to define what would be the distance of, let's say, this Y node from G. Let me zoom in a bit. Okay, so we have the Y node over here directly above G. So there are several different ways in which we could define the distance from Y to G. Okay, in this particular question we are asked to follow the Manhattan distance pattern. So are you familiar with what Manhattan distance is? Is there anyone who is not familiar? Okay, then let's just for the sake of completeness, let's discuss what it is. So Manhattan distance is basically a way of measuring distance that's based on the structure of Manhattan city. Okay, so Manhattan city is constructed blockwise. So let me show. Yeah, please go ahead. Mm-hmm. Mm-hmm. Okay. Mm-hmm. Okay. I see. That's yeah, that's a great suggestion. I agree with it. So yeah, I'll try to do that from next week onwards. I'll. Mm-hmm. Thank you. Sure. Yeah, I greatly appreciate your suggestion, and I'll try my best to incorporate that from the next week. Okay. So yeah, in that case, maybe I'll just go through what Manhattan distance is very quickly. So yeah, basically it's a block-wise system, and here we can assume that each of these small blocks that we have has a unit of 10. Okay, you can think of it as 10 centimeters, meters, kilometers, whichever you may want to consider. But each of these small blocks is a 10 cross 10 box. You can think of it in that way. And so the distance of y to g would be 3 blocks, right? We have to travel 3 blocks to reach g, so it will be 3 into 10, which is 30. Okay, so that's how we define the heuristic over here. And based on that, this question asks us which node has the largest heuristic value. Okay, so what would be the node that is having the largest heuristic value? A. That is right. A is the node that is having the largest heuristic value, and that is a value of 220, because we have to cover 22 boxes to reach from A to G. Okay, so this was a straightforward question, and I think that should be okay for all of you. If there are any doubts, please let me know. Cool. So similar to the uh, largest heuristic value, which was belonging to node A, which of the nodes have the smallest non-zero heuristic value? You can think of any unit for each of the box. We know that it is a 10 cross 10 box, but you can think of it as centimeter, kilometer, inches, whatever you want to consider. Y, that's correct. Y is the one that has the smallest non-zero heuristic value. That's great, which is 30. Okay, let's move on to the next question then, which deals with best first search. Okay, so does anyone remember what is the core logic of best first search? Mm-hmm. But okay, but is it always the case? Uh, uh-huh. But then in that case, what's the difference between best first search and hill climbing method? Hill climbing will also try to climb. That's right. So yeah, that's right. You're correct. I'll just make it put it in a more nuanced manner. So the data structure that best first search uses is a priority queue. So till now we saw queue, right, where the elements were inserted from the back of the queue and elements exited from the front of the queue. In a priority queue also a similar trend is followed. Just the thing is that when we insert elements, we insert them based on a priority, and that priority is given decided by the heuristic value in our case. Okay, that's the only difference. So yeah, this question tells us that uh, sure. So basically we have a priority queue. Okay, it's a queue structure where the elements are inserted based on the priority that they have, and that priority is defined by the heuristic value. Okay, um, so let's go through the um, example, the question, and hopefully that will get clearer to you. It is yeah, it's like that. Mhm. Okay, so let's go through the solution. Okay, during inspection, so yeah, in the map, starting with node S, list the first 7 nodes inspected. Okay, so again, we have to list the first 7 nodes that are inspected. During inspection, if multiple candidate nodes have the same estimated cost, then inspect those nodes in alphabetical order. So we are told that if we ever encounter a tie, let's say 2 nodes have the same heuristic value, right, or the same priority, then in that case, we have to break the tie by choosing the one that is alphabetically coming before. Okay, Uh, then it says that list the nodes inspected in the order they were inspected. So similar trend you have to follow as the previous questions. And if the algorithm terminates early, then we have to list down the nodes inspected up until termination. Okay, so let's do one thing. When we have to start with S, let's calculate the heuristic value for S and all the neighbors that S is connected to, right? So what is the heuristic value of S? Can anyone quickly tell me? Is it 160? Yeah, thanks. Yeah. So it's 16 boxes. So into 10 we will do. We have assumed that each box is 10 cross 10 units. So let's say it's 160. Okay. Then let's have a look at E. What is E? Is it 170? Okay, thank you. Then what about J? I think they should be 190, right? Okay. Then what about K? 120. Okay, and what about O? I think this should also be 120. Let me just verify. Yeah, 120, right? Okay, so there's a question on how we calculate this value. So we calculate this value using the Manhattan distance, and then we multiply it by 10 because we have assumed that each of these small blocks is a 10 cross 10 block. Okay, and yeah, for further explanation, like one of your friends was suggesting, this was discussed at length in the previous live session, right, by on Saturday. So I would recommend you check that out. If it is still unclear, please let me know. We can discuss it again. Okay, so these are the ones that we have at hand, right? So first we'll of course inspect S. Okay, let's make a tick mark over the one we have inspected. Okay, after S, these elements would be inserted in the priority queue based on their heuristic value, right? So which one would be which one would be explored next? What do you think? K, right? Because both of them have the lowest heuristic value of 120 and K comes before O in alphabetical order. So K will be inspected next. Okay, so let's tick on K. Okay, and let's look at the distance of the neighbors of K. Okay, so K is connected to F, Q, L and H. So what is F? F is 150, is it the heuristic value? Okay, let me know if I am making any mistake. Okay, then we have Q, which is 90, I suppose, right? Then we have L, which is 80. Okay, and then we have H, which is this 90 or 80? I think it is 90. Can you confirm once? Okay, great. That's great then. So now we have all these different elements that we have computed a distance for, and again remember we are following a priority queue, right? So which of these would be at the front of the priority queue? L, that's correct. L, that's right. L will be there, followed by H. That will be followed by Q. That's correct. So you get the idea. So this is where the best first search is differing from hill climbing. So what would have happened? So see, let's go to L then. L is the next node we are exploring. We have no doubts about that, right? Because we are at 80, which is the lowest heuristic value or highest priority. Now, what would the hill climbing algorithm would have? What would it have done at this point? Exactly. Exactly. So it will get stuck at L because there is no neighbor of L that has value lesser than 80, right? Whereas best first search, because it follows a priority queue, after L it will go to H. Okay, so after L it will go to H. Now let's take a look at the neighbors of H. So we have C and M, right? All others we have computed already. So for C, what is the value? Is it 130? 140, is it? Okay, let me correct that. Okay, and what about M? It should be 50, right? Okay, now we have a new most priority element which has 50 value. So M will go at the front of the priority queue, correct? Right? Because we were at H, right? While we were exploring H, we saw that M is also a neighbor of H, right? And M is having highest priority till now. So M will be shifted to the front of the queue, right? So next we will explore M. And how many elements have we explored till now? We have 1, 2, 3, 4, 5. Okay. Uh, let's have a look at the solution and see if we are going in the correct direction. Um, so in terms of the data structure that we follow, we are still following a queue, but the difference is that it's a priority queue. So that inclusion of that priority based queuing, I think, makes it somewhat distant from a traditional breadth first search. It's difficult to say whether it's closer to a breadth first search or depth first search. Let's think, we can think of it as something that's midway between both of these, like best of both worlds in some ways. Yeah. Yeah, we will add I as well as P based on their priority. Okay, so let's look at the solution. We have explored S, K, L, H, and M till now, right? So after M, we will explore P and then G. Okay, so I'm not completing the solution unless you want me to. Um, and this is the first 7 nodes that best first search will explore. And you can see that within the first 7 nodes explored itself, it's finding the goal node. Okay, whereas both depth first search and breadth first search couldn't find the goal node in the first 7 explorations. So you can already see that this is an improvement over both of them with respect to this example alone. Okay. Okay, so there's a request on how to calculate the heuristic value. I'll just show one example. Okay, let's consider this node. Um, let's consider W. Okay, we have to calculate the distance of W from G. Okay, and that we will do by measuring how many of these square boxes we have to cover while we go on the path from W to G. Okay, so this is the first box that we will cover, right, in this direction. Second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10th, 11th, and then finally 12th So we have to cover 12 boxes to go from W to G. Now it's not necessary that you have to do it in straight line and then first horizontal line and then vertical line. You could do this in any manner like this. You will always have to cover 12 boxes only, right? So because we assume that each of the box is 10 units in length, then we multiply 12 into 10 and we say that the heuristic value or the distance of W from G is 120. In the exam you will be given these boxes, I suppose, otherwise it would be difficult for you to calculate the distance, or the distance itself will be given to you, either one of those, I guess. Okay, so I hope best first search was clear. Any doubts there? Good question. Why can't we go through other paths? The reason is that this method doesn't allow us to go through other paths. If we choose a better method that will give us a more optimal path, then we'll follow that. Okay, so it's just a matter of what method we are using to solve our problem. In the coming weeks we'll see even more efficient algorithms, right? We saw some DFS and BFS kind of very deterministic algorithms, right? Then we saw some heuristic based methods that we are looking at right now. Then in the coming weeks we will also have a look at something that combines heuristic as well as the depth first kind of, or depth or breadth first kind of solution. You'll have a look at those kind of methods as well. Okay, so if this is clear, then let's go to the next question, which is about hill climbing. I think we covered this question as well while we were discussing the previous question. No, Ashwini, to answer your question in the chat box, this is best first search, BEST, not breadth first search. Breadth first search is different. The previous one was best first search. Let me just show it to you. Okay, and breadth first search is different. Okay, I hope that resolves any confusion. Okay, I showed the answer already. So yeah, as we discussed, when we are exploring the hill climbing algorithm, which will only to go to a next node if there is a improvement over the current node that we have. That's what I said just now, right? So if hill climbing sees that there is an improvement over the current node that it has, it will go over there in that direction. If it cannot go to any further place where there is an improvement, it will stop over there and say that it has terminated prematurely, which is what is happening over here. It went from S to K to L, and from L there was no other point where it could go to any other node with a smaller heuristic value than L, so it stopped over there, or the goal node. Okay, anything else in this one? Okay, if not, then great. Now let's go to the question on SAT. Okay, so I think this is kind of a preliminary step to what we will do when we follow beam search. Okay, so I think this will cover one of the requests about the beam search heuristic. Okay, so we are going to solve the SAT problem. Okay, so are you familiar with the SAT problem? Okay, so basically SAT stands for satisfiability. Okay, and let's look at this function over here, which is given by f. Okay, so this f is made up of 5 different variables which are a, b, c, d and e. Yeah. Oh, is it? I have moved to the next question. Um, okay. Okay, okay. Maybe you can, no, no, no problem. Maybe you can try rejoining once and see if it's better then. Okay. Yeah. So we have a function made up of 5 variables a, b, c, d and e. Okay. Each of these can take binary values, either a 0 or a 1. Okay. And I hope you are familiar with what these connectives are. These upward marked triangle and lower marked triangle. These are and or, right? Are you familiar with them? Okay, that's great then. So the triangle facing downwards, pointing downwards is the or, and the triangle facing upwards is the and. Okay, so from Boolean logic, we know that once these a, b, c, d, e, and this small kind of dash over before variable stands for not or complement of that, right? So if it's 0, it will be converted to 1. If it's 1, it will be converted to 0, right? So once we give a particular assignment to these a, b, c, d and e, this function f through all these different not and or and ands, this will also have a particular value, right? Either 0 or 1, right? Do you agree with me? And for whichever assignment will this function will have a value of 1, we will say that for that particular configuration it is satisfiable, right? F is having a value of 1. Now we want to find which particular configuration or which particular assignments of 0 and 1 to a, b, c, d and e will give us a satisfiable solution, right? And in order to achieve that, see all of these uh, small elements that are part of this first bracket, these are all connected by and operators, right? So if all of these small brackets evaluate to 1, then we would have 1 and 1 and 1 and 1 and 1 and 1, right? So f will evaluate to 1. If any one of these also evaluates to 0, f will evaluate to 0. Do you agree with me? So we can define our heuristic value in this case in terms of how many of these small brackets is evaluating to 1. Okay, for example, let's say our start node in this case is 1 followed by 4 zeros, which basically means that a takes the value 1 and then b, c, d, e take value 0 each. Okay, is the assignment clear in the from the starting node? Okay, then how many of these small brackets would be evaluating to 1? Let's have a look at that, right? So this first one will be 1 or not of b, which is not of 0, right? Which will be 1 or 1. So the first one will evaluate to 1, right? Then the second one will evaluate to not of 1, right? Which is 0, or d, which is 0, right? So second one will be 0. Similarly, b or c will be 0, b or d will be 0, not c or not d will be 1, right? Because this will be not of 0 or not of 0, which will be 1 or 1, which is 1. And then c or e will be 0. So out of all of these, 2 of the small brackets have evaluated to 1. So we will assign a heuristic value of 2 to this start node, which is 1 0 0 0 1 0 0 0 0. Okay. Now what we can do is we can flip the bits one by one. Okay, let me draw it. So we were at 1 followed by 4 zeros, right? This was our start node. Now how will we define the neighbors of this this node? Does anyone have any idea? That's right. That's right. Yeah, that's perfect. We will proceed in that fashion. So this is an example of SA, let's call it, by flipping the A note. Okay. So SA will be 5 zeros. Then similarly SB will be with B node flipped. So it will be 1 1 0 0 0. SC will be 1 0 1 0 0. SD will be 1 0 0 1 0, and SE will be 1 0 0 1. Okay. So let's write all of them down. SA was all 5 zeros. SB was 1 1 followed by 3 zeros. Please excuse my horrible drawing. SC will be 1 0 1 0 0. SD will be 1 0 0 1 0, and then finally SE will be this one. Right, now we know that. Let's use a different color to mark the heuristic value. Right, this had heuristic value 2. Right, now what will be the heuristic value for each of these 5 children that we have? Can you quickly calculate it and tell me? Yeah, yeah, sure. Let's so we had this function over here, right? And these are all basically connected by these AND operators, right? You see there are 1 2 3 4 5 different AND operators and 6 of these small brackets. In order for f to be equivalent to 1, right, we would need all of these small brackets to be evaluating to 1, right? So we will define the heuristic value as to be how many of these small brackets are evaluating to 1 given. Ha. Okay. So with the starting node, we saw that only this one, this A or not B, and not C or not D were evaluating to 1. So we gave it a value of 2. Ideally, we should have a value of 5, right? So let's see what SA will have. So A will have 0 or not B. So this will evaluate to 1, right? This will evaluate to 1 because it has a not A. B or C will evaluate to 0. B or D will evaluate to 0. This will evaluate to 1 because we have not of C or not of D, which makes 1 or 1. And this will evaluate to 0, right? So we have 1, 2, and 3 of these small brackets that have evaluated to 1. So this will have a heuristic value of 3. Agreed? Cool. Now similarly, let's find the heuristic value of the other nodes as well. So can someone quickly compute and tell me? I'm just being lazy here, but thanks for doing it for me. Okay, let me also check in the meantime. So we have only A and B as 1, right? So this will be 1, this will be 0, this will be 1, this will be 1, this will be 1, and this will be 0, right? So we have 1 2 3 and 4 to be 1, right? So this will have a heuristic value of 4. Okay, now what about SC? SC has A and C as 1, right? So again this will be 1, this will be 0, this will be 1, this will be 0, sorry, B and B or D would be 0, this will be 1 again, because not C will be 0 but not D will be 1, right? And then this will also be 1, right? So we have 1, 2, 3 and 4 again, right? 4 of these will be 1, so again we assign a value of 4 to this. Please correct me if I am making any mistake. Okay, let's have a look at SD then. So here A and D have assignments 1, so this will be 1, this will be 1, this will be 0, this will be 1, this will be 1, right? Because not of C will be 1, not of D will be 0, so 1 or 0 will be 1, and this will be 0. So we have 1, 2, this will be 0, 3 and 4 again. Am I correct? Okay, let's assume I am correct. I am very prone to making mistakes, so please let me know if I am doing any calculation mistakes. Okay, let's have a look at SE then, the last child. So here A and D have values 1, so this will be 1, right? This will be 0, this will be 0, this will be 0, this will also be 0, this will be 1. So we have only 1 and 2, only 2 of them will be 1, right? So this will have value 2. Okay, great. So we have found out the heuristic value of all of the children of S, right? Now we have to see what the question is asking us. Okay, the question only asked us what are the heuristic values of these. Okay, that's fine, we have already computed that. 2, 3, 4, 4, 4, 3. Did we do it correctly? Yeah, 2, 3, 4, 4, 4, 3. Huh? The last one, is it 3? Let's verify. Okay, this one is 1. Yeah, this one is, oh okay, this one is also 1. Correct. So it will be 3. Correct. So this is 3. Okay, so now that we have found all the heuristic values, what beam search would do in this case, it wants to maximize the number of the heuristic value, right? In this case, in the previous example, what we were looking at, we were trying to find the least heuristic value, right? Because the heuristic value was defined in terms of the distance from the goal node, and we wanted to reduce the distance from the goal node, right? Here we want to maximize the heuristic value. We want to make sure that as many of the small brackets, which are called clauses, I think, are satisfied, or they have a value of 1. Sorry about that. So what beam search will do, depending on what is the size of the beam that we are assuming, let's say we have 2 of them, right? I think this question was also raised in the previous live session. We have multiple candidates here, right? See, 3 of them have heuristic value 4. So which of them we choose? Let's say we randomly decide any 2 of them to choose. If we have a beam size of 2, let's say we choose SB and SD. Okay.
Sir, sorry to interrupt.
Yeah.
I haven't gone through the beam search part. Could you quickly explain it?
Sure, let's do that, because there was also another request. Um, so by the way, was this covered in the previous live session? Can you just confirm quickly? No. Okay, no problem. As in,
Previous session mostly
mhm.
climbing questions and heuristic function questions
I see, I see. Okay, okay, that's great. Um, which of these would have this? Would it be escaping local optima? Aha, so here we have beam search. So, aha. So here we the same SAT problem has been explored. Okay. Um, so here if we have, let's say, a beam width or beam size of 2, instead of looking at only one candidate solution in each step, right, as we go through the depths of the search space, we will explore two of them together, and those two would be forming our beam. Okay, so here if you see that we started with this gray node at the top, right, and we saw that these two blue nodes at the two extremes of the, which are the immediate children of the root node, they formed our beam. Okay, so we will explore these two further. Okay, so we will draw the children of these two further. So we will have uh, a number of children corresponding to both of these nodes, and then among all of them we will choose the next two most promising. Okay, that will be the beam in our next generation or next iteration. Okay, so you see it's moving in pairs of two as we move from each one iteration to another or one generation to another, right? Here you can also have a look at this particular case. I don't know if you can see my cursor. Is my cursor visible?
Yes, it's visible.
Okay, okay, that's great. So in this particular step, here in the previous step, we had selected this particular and this particular child as the beam, right? But in the next step, we don't consider any child of um this particular the leftmost constituent of our beam. Okay, because that's not promising. Instead we consider two of the children of the right side, right constituent of the beam, because those two are the most promising. So in each step we will consider the two most promising solution and then move ahead through the steps. This beam width could have been 3, could have been 4. If it was 1, then it will boil down to going through only one promising solution in each step. Okay, so this is like a brief overview of what beam search does, but yeah, I would encourage that you go through the uh, lecture videos by Professor Khemani to go find a more in-depth explanation.
Okay, I get it. And
Yeah.
why does it maximize the heuristic value?
uh, Here the problem demands that, right, here we want to achieve a state where all of these clauses evaluate to 1, right? So because we have defined the heuristic value as the number of clauses that are satisfied, or in other words the number of clauses that evaluate to 1, um, we want to make it as high as possible, right? Because only in that case would the whole formula be evaluating to 1, because they are all connected through ands, right? Even if one of them evaluates to 0, this whole formula would be switched off and it will evaluate to 0.
Okay, got it.
Okay, cool.
Sir,
Yeah.
sir, in this example you have shown,
Mm-hmm.
why this is stopped at the third level, sir? This level, 4, 0, 5.
Which one?
Why it is stopped? In this example, what you are showing in the slide now,
Uh-huh.
why it is stopped at this level?
Okay, let's have a look at why it stops. So here it says that beam search with width 2 fails to solve the SAT problem, starting with all ones. Starting with a value 3, the solution should be reached in 3 steps because it is hill climbing. In fact, the node marked star leads to a solution in 3 steps. Um, so here only the first 3 steps are shown to you, but it says that if it had explored this particular node instead, the one with 3 marked star, it would have reached the solution much quicker in the next generation itself. But because of the property of, yeah, exactly, however number of clauses we have over here, we have 1 2 3 4 5 6, yeah, 6 of them. But here, because we are exploring, we are being greedy over here, right? We are choosing the ones with 5 value. we see that in the next step we are not finding the optimal solution, so this can be extended further. We can still explore the ones with 5, but it will not terminate more probably in the coming future. It will go on expanding forever also. That is what is shown in this diagram over here, right? It looks at the best it will keep on expanding if if it doesn't reach the ultimate goal.
This is hill climbing, beam search, hill climbing. What is node search?
Uh, yeah, it's similar to hill climbing in that it is being greedy and it is choosing the
Beam.
with the improvement over the current current what to say current.
Because it is hill climbing, there is no further improvement in the nodes to choose.
Exactly. Yeah, yeah. That's the better reason than what I said.
But
Yeah.
here, how it is beam search? Because it is
Just because we are considering
beam width
two.
2. We are selecting only 2 nodes.
Yeah, we are considering two candidates at once. If the beam width were 3, we would have considered 3 candidates. Yeah, thanks for that clarification. And yeah, for correcting me as well. Yeah, the correct explanation for why it's stopping over here in the third step is because it can't move any further. There's no further improvement from here. Okay, so I hope that covers the beam search doubt. Anything else here? Okay, so that's all with the questions I had for today. So then let's go to the traveling salesman problem. Okay, because that was another request. Can you tell me which slide did we have that in? Did we have it in slide 5, this one itself, or was it later on? Ah, it's here itself. Okay. Uh, so sorry. So basically, the idea over here in traveling salesman problem is that we have a number of cities, okay, and we are also given the distance from one city to another for all the pairs of cities. What we want to do is we want to start from any one of the cities, okay, and we want to follow a path that covers all the cities exactly once, okay, and then comes back to the city that we started at, and it also does that in the least amount of cost in terms of the distance that we have to cover. Okay, so given a set of cities and given a distance measure between every pair of cities, the task is to find a Hamiltonian cycle having the least cost. So Hamiltonian cycle is basically uh, where we start from any one node of the graph, we cover all the other nodes exactly once, okay, and then come back to the starting nodes because we want to form a cycle, and we also do that while covering the least amount of distance moving from one city to another, right? That's what we want to do, and this is an NP hard problem. Okay, that is the overview of the traveling salesman problem. Now there are different ways to solve it. Okay, for example, there is this nearest neighbor heuristic. Okay, uh, where we start at some city and then we move to the nearest neighbor of that city. Okay, so let's say we start at this city over here where my cursor is. Let's say the nearest neighbor to this one is to the right of it, this one, and then let's say the nearest neighbor of this one is this one, and um, we keep doing that. But in case there are some outliers, okay, this method will get affected. Okay, in some event, let's say, where the outlier is the nearest neighbor, it will go to that one, and then this will affect the final solution. So there are different approaches to improve this heuristic. There are some greedy heuristic where we sort the edges, and then with the shortest edges is it selected first, and then we have to make sure that the loop is not closed prematurely. We have to cover all the cities, and different possible methods are there, right? There are some methods like genetic algorithms as well that we will probably explore in week 4, right? Um, there is one savings heuristic as well. There are several different methods to solve this particular problem, and these are basically the different paths found or tools found by different heuristic or employed by different heuristic methods. So greedy tour follows something like this, nearest neighbor follows something like this, right? Savings tour and optimal tour respectively. So this was an overview of the traveling salesman problem. Is there anything specific that you want me to discuss? Because then I would also have to go through that material before I explain it, understand it myself, and then explain it if possible.
Sir, I hope it is easy for you. Please go to practice assignment week 3 PA TSP. Please, sir, once.
Week 3 PA.
Practice assignment TSP.
This one?
Week 3.
Mm-hmm.
Yes, sir. Yes. In that fourth question, sir.
Okay.
Second note question. For n greater than 4, when a
Mm-hmm.
graph has n nodes and n edges, every node has exactly 2 edges connected to it.
Mm-hmm.
The answer for this is second option. The graph may or may not depict a, but I think the first option is correct, but the answer given is second option. Why, sir?
Okay. Let's draw a graph like that. So let's say we have 5 cities. Okay. And then the question tells us where a graph has n nodes and n edges, and every node has exactly 2 edges connected to it. So we have n edges, so we will have 5 edges, and every node has 2 edges connected to it. So this could be one, right? Let's name the nodes. So let's name it 1, 2, 3, 4, and 5. And then let's draw the edges with a different color, just for the sake of clarity. Maybe blue. Okay, so let's say these are 2 edges, these are 2 edges. We have only 5 edges in the graph, remember, right? Because we are told that we have n nodes and n edges. Let's say this is our first edge, this is our second edge, this is our third edge, this is our fourth edge. Oh, okay, so we have 5 edges. Okay, now so is this satisfying all conditions of a tour? Let's have a look at that. Let's go over here. That is not defined here. That's okay. We know the conditions more or less. Let's have a look. So basically our condition, let's say we start from this one node over here. We want to travel each node exactly once, right? So we go from 1 to 2, let's say, then 3, then 4, then 5, and then back to 1, right? And this is the only way. Mm-hmm. Yeah, in this case it should work. This would have a tour, but what is the correct option? It said the graph may or may not depict a tour of n cities, right? So is there an arrangement of these 5 edges possible that makes this cycle or tour impossible? There must be something like that, right? That's why they're saying that it may or may not be possible.
So this question maybe corresponds to the given set of cities location problem, sir.
uh,
Beginning.
in the beginning, no, I think it's general for n, right?
Can you show
Can
the
you tell
question,
again,
please?
please?
Yeah. for n greater than 4 when a graph has n nodes and n edges and every node. Yeah.
Do we need to come back to the starting position?
mm, if you have to complete a cycle if you have to complete a cycle, then I guess yes.
Then I think if we take n equals to 6, we can come up with a counter example where there is not a complete loop.
Uh-huh.
No, no, it's given n no n nodes, n edges. It's correct.
um,
Two edges connected to each. Two edges connected. That is the condition for traveling
okay,
cell
but
space.
let's try to rearrange our edges and see if things still make sense. Okay, let's say this is connected to this one, then this would have three edges connected to it, right? um,
Can you not see the board?
oh, sorry about that. Now I think should be visible.
Yes.
Okay, is there any other arrangement where we can still have the condition satisfied? Something like this, maybe.
Yes, sir. So may or may not.
I mean, this is one possible configuration, but here I'm going on a limb and assuming that we have edges back and forth from the same node, which,
Both directions.
yeah, that's not given.
Not traveling from alpha into one into the other the second time. So in that case, second option right for this.
But let's see if there are any other arrangements possible also. About what one of your friends was suggesting about if we have n equals to 6, right? Um, Maybe we'll be able to find some case there where this condition is violated. But is that what you were referring to? Uh, Sorry, I don't remember who spoke up.
Yes, but I mismatched the question. It's difficult to get a counter example, but we can try.
We can try, but what I was thinking is that if it's applicable for n equals to 6, it should also be applicable for n equals to 5, right? Because the question tells us for any n greater than 4. So it should be applicable for n equals to 5 as well.
Okay.
Yeah.
Okay, sir. No problem. Let us discuss this later. Then week three, PA TSP savings test, next assignment.
Mm-hmm. Yeah. So what I would suggest is just to give us a sort of completion to this the discussion. Um, this is okay. This, let's say that this is our temporary understanding of why second option is the correct one. I would also request you to please post this question as well as our attempted solution on the discussion forum so that Bhaskar and sir can verify and say whether our understanding is correct or not. Okay. So any one of you can take up the responsibility and post this in the discussion forum along with our attempted solution.
Okay, sir. Post.
Okay.
I
Also,
think I found a counter example.
okay, then yeah, tell me.
Can you draw like n equals to 7 with
Okay.
7 vertices?
Sure, let's draw that. Let's have 1, 2, 3, 4.
Oh, I think it won't work. I'm sorry.
Okay, no worries. It's okay. We can think about this offline as well, and maybe our assumption, what we think right now, is correct. Maybe it's not correct, but let's think a bit more on it offline. And in the next week, hopefully, one of us will have an explanation.
Okay.
Okay.
Sir, what is the correct answer for question number 3, sir? Second,
Question number 3,
same question.
the one that we were discussing, right? Yeah, it says that this one, the graph may or may not depict a tour of n cities.
Correct.
Yeah.
Moving to question number 3, sir. Simple question only. But how to initiate question question means how to take the starting point or starting city, sir? Not considering any
You can take any city as starting city because our goal is to cover all cities, right? So no matter which city you start from, you should cover all. You should satisfy all the conditions of the traveling salesman tour. You have to cover all cities. You have to cover all cities exactly once. um, and so that gives me a hint, because we have to cover each city exactly once. Maybe we don't need to come back to the starting point, right? Because then we would be visiting that city twice, don't you think?
The traveling salesperson problem
Come
is
back to home.
basically come back to starting point first.
Yeah. Okay, let's think about this offline. I think I also need to give some more time to it.
Sir, my doubt is it is a greedy heuristic
Mm-hmm.
regarding traveling distance part,
Yeah.
or it is mainly the perception that very content
Uh, I also have to check for that what exactly is done in greedy heuristic. Based on the definition, it seems like yes, we will be greedy and we will sort the. Okay, so it says that sort the edges at the shortest
Shall
available
I
edge.
answer this question, sir? Shall I give the answer?
Sure, please go ahead.
Actually, it is greedy heuristic. The algorithm says sort the edges first. So from the edges, we have to take the least distance. The table is given. The least distance is E to G. So we edit from the given twos. There are three twos given in the question, which joins E to G. Those two options, 2 1 and 2 4 is correct.
Mm-hmm.
Next distance, shorter distance is 22, which is E to D. Then which connects E to D. After that, next shorter distance, like that we have to go. So we are getting 2 1 as the answer. The objective is we have to sort the edge. Then we have to start with the shorter edge.
That's
First distance matrix.
that's correct. That thanks for the explanation, Jayanti. That yeah, that was a great explanation. So Khalid, I think that helps.
yes, sir.
Okay. Uh, okay. So anything else here? I think there was one question that was requested from the next PA, right? Savings heuristic, is it?
Yes, yes, savings heuristic.
So
Last
yeah, yeah. So
last two questions, 12, question number 12 and 13.
mm-hmm. So this is one heuristic where I am also not very well read on. I need to revisit and see what exactly savings heuristic is. So yeah, just give me some time and maybe next week we can discuss this. I hope that's okay.
Okay, sir. Thank you, sir.
Yeah,
Question number 12 and 13, sir.
sure. I'll make a note of that
Sir,
because.
please go through this.
Mm-hmm.
Question number 4 up to 10. Same city, 4 up to 10, sir.
Which assignment?
The same assignment.
This one. Okay.
Yes, yes. Question number 4 up to 10.
Mm-hmm.
Base city is common, sir.
Okay.
Only 10 only we are getting the answer. Otherwise, we are not getting the answer.
I see. Okay, I'll go through this because I also honestly haven't been in touch with the course for a long time, right? So the last time, yeah. So yeah,
Because it is a coursework for my PhD program. That's why I am telling, sir.
no, it's okay. That's understandable. Yeah. Okay. Anything else that you would like me to discuss? Okay. If not, then maybe we can close the session for today. And yeah, I'll subscribe to the discussion forum, and uh, if you have anything, please post it over there. We can follow up with that in the next session.
Sir, can I ask question now?
Yeah, yeah. Please go ahead.
Sir, in the weekly practice assessment,
Mm-hmm.
uh, this question number 4, I think.
Which one? In this one?
Yes, weekly heuristic function.
This one?
Question Q. Yes, sir. In that question 4 and 5. In the question,
Mm-hmm. 4 and 5.
no, sir.
Is it this one? Then next two.
heuristic function example 2.
Example 2. Okay. Is it this one?
Yes, this one.
Okay.
This is question number 4 and 5.
Mm-hmm.
It is saying that ST and NT code to be calculated. He has defined ST in the question number 1.
Mm-hmm.
This code in the question number 2.
Okay.
I am asking what is the correct way to understand about the location of A with position Q. Position Q
Position Q of A.
for A, yes.
Okay.
Entry value and initial value.
Okay.
Number of misplaced blocks not in final. Whether do we need to consider A in that or not?
Okay. Let's have a look at what is the final configuration that we want to attain. So every block has a level number. A block resting on the table is at level 1. A block resting on level 1 block is at level 2, so on. So level numbers are like floor numbers in a skyscraper. Okay, so this is the start node and this is the goal node. Okay, so in the goal node A has level what? 1 2 3 4 5. Okay, A is at 5. So number of misplaced blocks not in final position. So according to H3, A is not in a correct position, right? A is not in a.
Negative, then answer will not come.
Is it?
Only F and E is not in correct position. F.
Okay. Only F is in the correct position, right? F is supposed to be at the bottom, and D is supposed to be at the bottom. C is supposed to be above that, and B is supposed to be above C, right? So F, B, C, D. These are the correct ones. A and D are not in the correct positions, right? Yeah.
Coming to H4 also same.
Number of correctly placed blocks in the number of correctly placed blocks in final position. Okay, so in that case B, C, D and F would be the number of correctly placed blocks, right? So 4 would be the value for Q, for the configuration Q. Does that make sense?
Okay, okay, sir.
Okay.
Can anyone tell the answer from the group?
Answer, I think because this is a practice question, it will be available, right?
Yes, but I entered in the question 5.
Okay, it's 5.
Oh,
So we have to enter for all of them. So just check whether.
some random value.
No, it wouldn't be random value. Let's enter something random and check if.
Question number 6, sir. It is 6445 445.
Okay, so for Q, it would be 6444, right? 4 is what we got for Q.
Yes, sir.
Yeah, so that's correct, right?
Right, right.
Mm-hmm. Okay.
Sir, sir, next assignment, sir. We
Yeah,
have keep the idea.
sure.
Practice assignment, hill climbing and west coast search.
Okay, where is that?
Practice assignment.
Mm,
Hill climbing and west coast
this
search.
one?
Below that one. Yes.
Mm-hmm.
Sir, if I am in this graph, sir,
Mm-hmm.
graph this is given.
Mm-hmm.
In this, if I am asked to try and find a TSP tour using only edges in the map, what does it mean, sir, actually?
Uh, you have to find a TSP tour using only edges.
Yes, sir. That means what?
Uh, then see if so there are many extra edges over here, right? This wouldn't be forming a tour if we have all the edges. So see if we can remove edges that are not necessary and still have a tour formed. That is, every node is visited and exactly once, and then a cycle is formed.
So S, C, A, B, F, J, M, P, Q, R, N, only the outer nodes.
No, but we had to cover all nodes, right? Because if we are considering all nodes to be cities, then all cities should be visited, right? as per the condition. So see if that is possible. Based on what you told me, I think that is what the question asks. But yeah, I think we can think a bit more about it. Okay.
So internal nodes also we have to consider for that.
All nodes. TSP problem says that TSP problem says that we have to visit all nodes. It doesn't matter where it is placed, because uh, there our requirement is to visit all nodes, right? So no matter where they are placed, we will have to visit them. Yeah. Okay. Sure. Anything else? Okay. If there's nothing else, then maybe let's close the session for today. And yeah, let's meet next week, same time. Okay.
Yes, thanks.
Okay. Thanks for attending.